And the crazy part is, that's just the training data. Think about the compute required to actually use a model with a trillion parameters. We're talking exaflops of processing power.
Exaflops. So more than just a few GPUs in someone's basement, I'm guessing.
Just a slight upgrade needed. We're talking entire data centers dedicated to a single model. And it's not just the hardware, it's the software that coordinates all that processing. That's where the real magic happens.
Okay, so we're talking about distributed machine learning on a scale most of us can barely imagine. But why does it even matter? I mean, what breaks if we don't figure out how to scale to these massive models?
Think about the state of AI right now. The most impressive models, GPT-4, Gemini, Llama 3, they're all pushing the boundaries of what's possible. Without distributed training at this scale, we'd be stuck with models that are significantly less capable, less accurate, less able to understand and generate complex text, images, or code. Imagine a world where your search engine is just slightly dumber, or your translation software is noticeably less accurate. That's the world we're facing if we don't crack this.
So it's not just about bragging rights, it's about enabling the next generation of AI applications. But what are the fundamental challenges here? What makes training a trillion parameter models so different from training something smaller?
It boils down to three main things: communication, data parallelism, and model parallelism. Let's start with communication. Imagine you're trying to teach a class of 1,000 students, but you can only talk to one student at a time. That's essentially what happens when you try to train a massive model on a single machine. You need to distribute the work across multiple machines, but then you have to deal with the overhead of communicating between them.
Okay, so each machine has a piece of the puzzle, but they need to constantly share information to stay in sync. That sounds like a huge bottleneck. What kind of data are we talking about here? Is it just gradients?
It's gradients, yes, but also model parameters themselves, especially in certain strategies. And the sheer volume of data being exchanged is staggering. Think about it. 1 trillion parameters, each represented by 4-byte floating point number. That's 4 terabytes just for the model itself. Every time you update the model, you need to somehow communicate those updates across the entire cluster.
So you're not just sending a few numbers back and forth, you're essentially broadcasting a massive file every single iteration. What kind of techniques companies like OpenAI or Google use to minimize this communication overhead?
One key technique is gradient compression. The idea is to reduce the size of the gradients before sending them across the network. For example, you can use techniques like quantization, which reduces the number of bits used to represent each gradient value. Or you can use sparsification, which involves only sending the most important gradients and ignoring the rest.
But doesn't that introduce some loss of accuracy? I mean, if you're throwing away information, wouldn't that affect the final model performance?
Absolutely. There's always a trade-off between communication efficiency and model accuracy. The trick is to find the right balance. And that's where a lot of the research and engineering effort goes. Companies like Google are constantly developing new compression algorithms and communication protocols to minimize this overhead. They use things like specialized network hardware like InfiniBand and optimized communication libraries like NCCL to squeeze every last bit of performance out of their infrastructure.
Okay, so communication is a huge challenge. What about data parallelism? I understand the basic concept, splitting the training data across multiple machines, but what are the nuances when you're dealing with trillions of parameters?
With data parallelism, each machine has a copy of the entire model, but only sees a subset of the training data. Then the machines independently compute gradients on their respective data subsets and then average those gradients together to update the model. The challenge is ensuring that each machine is working on a representative sample of the data and that the gradients are averaged correctly.
So you need to make sure the data is shuffled properly to avoid bias. What happens if one machine gets stuck processing a particularly difficult batch of data? Does that slow down the entire training process?
Exactly. That's what's known as a straggler problem. One slow machine can hold up the entire cluster. To mitigate this, companies use techniques like asynchronous stochastic gradient descent, which allows machines to update the model independently without waiting for all the other machines to finish.
But doesn't asynchronous stochastic gradient descent introduce its own set of challenges? I mean, if machines are updating the model independently, wouldn't that lead to inconsistencies and potentially slower convergence?
It can, yes, but there are ways to address those challenges. For example, you can use techniques like gradient clipping to prevent individual machines from making overly large updates to the model. Or you can use techniques like momentum to smooth out the updates and prevent the model from oscillating too much. Think of it like trying to steer a boat in choppy waters. You need to make small, gradual adjustments to stay on course.
Okay, so communication and data parallelism are two key challenges. What about model parallelism? I've heard that's essential for training the very largest models.
Model parallelism is where you split the model across multiple machines. Instead of each machine having a copy of the entire model, each machine only has a piece of it. This is necessary when the model is too large to fit on a single machine. There are two main types of model parallelism: tensor parallelism and pipeline parallelism.
Can you explain the difference?
Tensor parallelism involves splitting individual layers of the model across multiple machines. For example, if you have a large matrix multiplication operation, you can split the matrix across multiple machines and have each machine compute a portion of the result. Pipeline parallelism, on the other hand, involves splitting the model into a pipeline of stages, with each stage being processed by a different machine.
So it's like an assembly line where each machine is responsible for a different step in the process. That sounds like it could be quite efficient, but also quite complex to implement. What are some of the challenges with pipeline parallelism?
The biggest challenge is dealing with pipeline bubbles. These are periods of time when some machines are idle while waiting for data to arrive from the previous stage in the pipeline. To minimize these bubbles, you need to carefully balance the workload across the different stages and use techniques like micro-batching to overlap the execution of different stages.
So you're constantly balancing act between communication, data parallelism, and model parallelism. You're trading off different types of overhead to find the optimal configuration for a given model and infrastructure. But here's where it gets interesting. Pause for effect. Doesn't all of this sound incredibly similar to general distributed systems problems? Like, aren't we just reinventing the wheel here?
That's the exact point, and it's the thing most engineers miss. The core principles of distributed systems, things like consistency, fault tolerance, and load balancing, they all apply to distributed ML training. We're just dealing with a different type of workload. Think about Netflix, right? They've been dealing with massive scale and distributed systems for years. The techniques they use to stream video to millions of users are surprisingly relevant to training large language models.
So, someone who's an expert in building scalable web services or distributed databases could potentially transition into the field of distributed machine learning relatively easily.
Absolutely. The underlying principles are the same. It's just a matter of learning the specific tools and techniques used in the ML domain. And that's why I think this is such an exciting field to be in right now. It's bringing together the best of both worlds, the theoretical foundations of machine learning and the practical engineering skills of distributed systems.
So, we've covered the challenges and the connection to broader distributed systems principles. What's the practical takeaway here? What should a software engineer do differently after listening to this?
First, understand the trade-offs. Don't just blindly throw more hardware at the problem. Think critically about the communication overhead, the data distribution, and the model parallelism strategy. Every decision has a cost, and you need to weigh those costs carefully. It's like choosing the right tool for the job. A hammer is great for driving nails, but it's not so good for cutting wood.
Makes sense. What's the second actionable item?
Second, embrace the existing tools and frameworks. Don't try to build everything from scratch. Frameworks like TensorFlow, PyTorch, and Horovod provide a lot of the building blocks you need to get started with distributed ML training. They handle a lot of the low-level details like gradient aggregation and communication, so you can focus on the higher-level aspects of your model and training pipeline. It's like using a library to avoid writing the same code over and over again.
Good point. And the third takeaway?
Third, learn from the experts. Read the research papers, attend the conferences, and follow the blogs of the leading researchers and engineers in the field. There's a wealth of information out there, and you can learn a lot from the mistakes and successes of others. Think of it like standing on the shoulders of giants. You can see farther and go further by building on the work of those who came before you. Look at what companies like Meta are publishing about their efforts to scale models.
So, understand the trade offs, embrace the existing tools, and learn from the experts. Sounds like a solid plan. So, to wrap up,
Not so fast. One more thing. Remember that scaling is not just about size, it's about efficiency. A poorly designed system with 1 trillion parameters can be less effective than a well-designed system with 1 billion parameters. Think of it like a sports car versus a monster truck. The sports car might be smaller, but it's often faster and more agile.
okay, now we can wrap up. That's a great point. It's not just about the number of parameters, it's about how you use them.
Exactly. And if you can master the art of distributed ML training, you'll be well equipped to build the next generation of AI applications.
So, scaling to 1 trillion parameters isn't just about more machines, it's about smarter systems.
Precisely.